Today, I'm going to introduce how to do option pricing by using Monte Carlo simulation method. First, I'm going to talk about what is Monte Carlo method. Suppose we want to know the expectation of gx, but we don't have a closed form of the integral. What we can do is to estimate the expectation by using numerical method called Monte Carlo. The idea of Monte Carlo is to generate n random numbers from distribution f, x1 to xn. And for each random number x we generated from distribution f, we will have a corresponding gx. Then we can use the mean of the sequence consists of all the gx as an estimator for the expectation of g. In summary, Monte Carlo methods are a broad class of computational algorithms that relies on repeated random sampling to obtain numerical results. Their essential idea is using randomness to solve problems that might be deterministic in principle. They are often used in problems that are difficult or impossible to use in other approaches like what we are trying to solve. Later, you will see that we are trying to figure out the expected value of ST, which is the stock price at the time we're interested in. It will be very difficult to obtain the answer by integration, but we can easily get an estimation of the expected value of the stock price by using Monte Carlo method. Now we assume that stock price follows a geometric Brownian motion. Thus, it follows the stochastic differential equation, where Wt is a Brownian motion, or Wiener process. By solving the stochastic differential equation, we have the relationship between the stock price of the time we're interested in and the initial stock price. Now we will try to simulate stock price by using Monte Carlo method. We noticed that Wt is a Brownian motion. Thus, the unconditional probability density function of Wt follows a normal distribution with mean equal to 0 and variance equal to t. Thus, we can rewrite the Wt term to square root of t times c, where c follows the standard normal distribution. Then we can begin to model the stock price by using Monte Carlo method. The first step we're going to do is to generate n random numbers from our standard normal distribution z. Then we can calculate our corresponding STs and use the mean of STs as an estimator for the expectation of ST. This is the R function I coded to simulate stock prices by using Monte Carlo method, using the stock, which means initial stock price, sigma, which is annualized standard deviation of daily return, strike, which is our target price for a call or put option, TTM, which means time to maturity, RF, which is the annualized risk-free rate, num.sim, which is the numbers of simulations we generated, and option equal to 0 for a call option, or 1 for a put option. Also, we consider the discount of the price to the present, which is pv.option, inside our R function. Inside our option pricing MC function, first, we calculated R, which corresponds to mu minus sigma squared over 2 times t in our formula. Then we calculate SD, which is the sigma times square root of t. Now we can simulate the stock prices by using Monte Carlo method. We're going to generate random numbers from a normal distribution with mean equal to 0 and variance equal to 1, num.sim times. Now, we have a sequence of TTM prices with length equal to num.sim, which is a sequence of stock prices corresponding to different numbers we generated from our normal distribution. Now, we need to consider two different cases. The first one is a call option, which gives the buyer the right to buy a stock at a specified price. We know that the intrinsic value at maturity of a call option is equal to the maximum value between 0 and ST minus K, where ST is the stock price at time to maturity, which is the TTM price in our case, and K is the strike price of the option. In R, we can use the Pmax function to calculate the maximum between 0 and ST minus K for each value within our TTM.price sequence. Then, we can calculate the discount of each value to the present by times e to the power minus mu times time to maturities to our TTM.option sequence. For put option, which gave the buyer to sell at a specified price. In this case, the intrinsic value at maturity is the maximum between 0 and strike minus TTM the price. Everything else is the same. In the final step of our function, after we got the PV.option sequence, which is the discounted value, we can use the mean function in R to estimate the value of the option. Now I'm going to demonstrate how to simulate the stock price using our option price MC function by a simple example. Suppose we have a hypothetical option with strike price of $300, years to maturity of 2.5 years. The initial stock price equal to $398.79. Annualized standard deviation of daily return is 32%, and the annualized risk-free rate is 1%. For the call option, we put the stock equal to 398.79, sigma equal to 0.32, strike equal to 300, TDM equal to 2.5, RF equal to 0.01, lambda sim equal to 10,000, and option equal to 0. For the put option, we have stock, sigma, strike, TTM, RF, lambda sim. They are the same as the call option, but the option equal to 1 in this case. From the output of our R code, we can see that our estimation for the value of a call option is $135.6813, and the value of the put option is $28.74931.